Namaskara. In this session, we will complete our discussions on Huffman code. We have as an input a character set C, which has got, let us say, character C1 to Cn. Each character has got certain number of times occurring in a character file. Okay? The frequency is denoted by f of C of I. So there is a huge character file that has the character C1 to Cn, where Ci occurs Fci times. So this is the character file, and I want to convert this into a binary file and store this. Now I want the size of my binary file to be as small as possible. That is a minimization problem. Okay? So each character C has got a corresponding code whose size of the code is denoted by LC, length of the code. Okay? LC denotes therefore size of the file size of the binary file or the coded file is sigma I equals 1 to n of LCI times f of Ci. There is a neat way to handle the kind of coding scheme that we are going to using a full binary tree. Okay? The full binary tree is called the Huffman tree. It is a full binary tree. Full binary tree means every node has got 2 or 0 children. That is called full binary tree. All internal nodes have 2 children. Of course, leaves have no children. Therefore, a tree of this kind is called a full binary tree. Every full binary tree, okay, a full binary tree with n leaves will have n minus 1 internal nodes. It is a basic property of a full binary tree. And the Huffman tree, the leaves of Huffman tree are associated with characters. So each leaf is associated with some character Ci. When you associate a leaf with a character, this association generates the corresponding code. Okay? So the path from root to the leaf associated with the character C defines the code for C, for the character. So how is this defined? If the path from root to the leaf will be made up of the right child and left child walk through. Okay? So any we associate anything going to the left, we will associate 0, anything going to the right. Therefore a path of this kind will define 1, 1, 0, 1. Therefore, this will correspond to, when you take the right child, when you go from a node to the right child, the edge will be associated with the bit 1, and when you take to the left, we associate 0 to such an edge. Therefore, the path will have several right edges and left edges that will correspond to a 0 1 sequence, and that is the code. Therefore, this is the code for this. If this is the character, then this will be the code for the character. Okay? So, this is how we are. So, once we have the tree, we can talk of the size of the binary file in terms of the tree parameters, because length of the code is nothing but depth of the leaf associated with the character C, right, depth of the leaf associated with the character C. That is a length. The exact 0 1 depends on the left or right turn, but the length is just how many edges you have walked over. That defines the length. It's the depth of the leaf associated. So, what you can write, the formula sigma LC f of C, C belongs to the character set, can be written in an equivalent way. Sigma depth in the tree of character C, frequency of C, C belongs to the character set. So, the formula for the cost of the code can be represented in terms of a tree parameter, namely the depths of the leaves. So, we are interested in construct an optimal tree. So, what do you mean by optimal tree? Optimum tree means this cost is minimized. A tree for which this cost is minimized. This is input. Character set under frequency is input. You have to find a tree with n leaves, and you have to associate with the leaves the characters in such a way that this quantity is minimized. So, how do we approach this optimization problem? Here is the greedy strategy. We are going to build a full binary tree in n minus 1 stages. Recall that you have n minus 1 internal nodes. Those internal nodes are going to be identified by this process. Okay? We refer the internal nodes as super nodes, and we use the symbol Z1, Z2 to Zn minus 1 for internal nodes. We are also referring them as super nodes. So, each node will have a character associated with it. Okay, let us say a character and the frequency. The super nodes have the characters Z1 to Zn minus 1 associated with it, and it is the weight associated with the node is some of the weights of the children. Okay. So, these characters are all only for algorithm or for the purpose of understanding and other things. Okay. So, you are not going to generate any of those kind of things. We can they are not the characters that are going to be used in the applications. It is just used for the purpose of describing the algorithm and discovering the code. The original character and character file codes are this. So, we have an example in which the character set was A, B, C, D, E, and F. Their frequencies are 45, 12, 13, 16, 9 and 5. With these frequencies, we create a supernode in the following way. Okay, you merge two nodes under a supernode. Put the smaller one on the left, larger one on the right, and create a supernode. Okay, so we have already demonstrated that process, and then we have created a tree and shown that its cost is found to be less in the example that we have seen. Now we have to show that it is optimal. Okay, we are going to show that this is optimal. The proof technique is an interesting proof technique. This proof is called the exchange argument. Basically, what we are trying to do is we do what is known as a cost preserving transformation over an arbitrary optimum solution and transform it into the form of the greedy solution that is constructed by the algorithm. So let T be the tree constructed by the greedy algorithm. Let T star be an optimal tree. We want to show that T is same as not T is not same, the cost of T is same as cost of theta. We want to show cost of T is same as cost of T star. That is, this is also an optimal tree. There may be several optimal trees. You have identified through this greedy algorithm an optimal tree. That is what we want to argue. So what we are going to do is we will do a series of transformation, cost preserving transformation. So from T star you construct T star dash, from there T star double dash, finally it will come to T. Because this transformation is cost preserving, cost of T star dash is same as cost of T star, which is same as cost of T star double dash and so on, and cost of T. That way we are going to argue that this is optimal. So our greedy algorithm, the tree generated by the greedy algorithm has got an interesting structural property. Namely, the lowest cost ones, okay, the smaller or the lowest cost ones are at a greater depth. The high cost ones will be at a smaller depth. The reason is intuitively clear, right? If A in our example were at a deeper position, its code will be longer, and if its code is longer and that many times that long code will appear in the representation. So high frequency characters must have a small code associated with them. Low frequency one, we can afford to have a slightly longer code for them. So in varying length code, the intuition is the high frequency ones will be given shorter code. So in our example, A received a code with a single bit because it's overwhelmingly large frequency you have. So it has got a very short code word for it and so on. And E and F, they are very low frequency, so their code words are 4 characters, but still we got advantage. Okay, so we have to formalize this intuition. So how do we go about describing this transformation? What we will do is we will bring the 2 low frequency characters. Okay, let us assume that let X and Y be two characters with lowest and second lowest frequency. That means frequency of x is less than or equal to frequency of C for all C belonging to C. F of y is less than or equal to f of C for all C belonging to C minus x. This is the minimum, this is the lowest, and this is the second lowest. Other than that, you remove that and again find the minimum, and that will give you the second lowest. These are the two characters. What we want to show is that they occur together and they are at the lowest level. Right? All characters are associated with leaves, but these are all the ones that are at the lowest level, the one that has got maximum depth. Okay, so x and y are together and they are at the lowest level. They are at the lowest level. So the scenario could be, suppose the lowest level has got some other character. Okay, let us take this. Just as an example. Okay, so this is x. This is at a higher level, lowest level. Let's say this is A and B. This is, let's say, y. X is at some depth, but A and B are deeper. Okay, so assume, if possible, suppose x and y are not at the lowest level. If they are already at the lowest level, nothing to argue. If they are not at the lowest level, they are at a higher level. They are the leaves at a higher level. There are some leaves at still lower level like this. Okay, assume if possible, x and y are not the leaves at lowest level, and let A and B be the leaves at lowest level. X and y have got the lowest frequency. So f of x comma f of y, they are less than or equal to f of a. F of x and f of y is less than or equal to f of b. These are the smallest and second smallest. So all others have a frequency. It's an important property by our assumption. And we are assuming that x is not at the lowest level. Therefore, depth of A in T is greater than depth of x in T. X is not at the lowest level. At the lowest level, there are some other characters. A, let us say, depth of A is. Similarly, depth of B is greater than depth of y. So these are the four facts we have about x, y, a, b. Similarly, depth of a is greater than depth of y, and let us say this is how the optimal tree is. Now we will swap, that is we are going to exchange. The cost preserving operation is the following: change A and X, call the resulting tree as T dash. Okay. So, call this tree as T and call this tree as T dash. So, you have an optimum solution and you have another solution in which the label of X and A are exchanged. My claim is that if T is optimal, T dash is also optimal. Okay. That is why it is called the cost preserving. If T is optimal, then T dash is also optimal. That is the reason why this exchange is a cost preserving transformation. It preserves the cost. Okay. So, how do you show that if T is optimal, T dash is also optimal? I am going to show that C of T is greater than or equal to C of T dash. C of T is, however, since T is optimal, C of T strictly greater than C of T dash is not possible, because T is optimal. Something smaller than that is not possible, that is the minimum. So, it is greater than or equal to, you are proving, you are ruling out the possibility of greater than. Therefore, this implies C of T equal to C of T dash. That means T dash is also optimal. So, from T I have changed something, I got T dash, but that is also optimal. This is the first thing that we will prove. This exchange is cost preserving operation. So, how to prove that C of T is greater than or equal to C of T dash? We will show that C of T minus C of T dash is greater than or equal to 0. This we will prove. That is because C is a linear combination, C dash is a linear combination. So, it is good to try this out. C of T minus C of T dash is greater than or equal to 0 is what we are going to show. So, what is the difference between T and T dash? If you look at the difference between T and T dash, the structure is same. So, for all other nodes, their depth, their code, everything will be same. For example, for B, the code there and code here will be same, the same path. Okay? The codes will remain same. Therefore, for all other characters, the code word as well as, of course, the frequency is a part of it. Code word being identical, when you subtract from the cost, cost is the sum of those things. When you subtract, all of them will vanish. Now, C of T minus C of T dash is equal to, okay, all terms other than X and A will vanish, because for X and A you have different expression, but all others it is same, therefore they will cancel out. So, A was earlier is equal to a length of length of the code word x times frequency of x plus length of the code word a times the frequency of a. This is how it was in T. This is C of T. Therefore, we write like that. The length of the code is nothing but depth. Okay. So we will write in terms of the tree parameter. Ct is depth in T of x times frequency of x plus depth in T of a times frequency of a. These two terms have changed. All others are same in T and T dash. Therefore, minus depth in T dash of x times frequency of x plus depth in T dash, sorry, minus, because minus Ct dash a times f of a. This is what Ct and Ct minus Ct dash. All other terms are identical and they get cancelled. Therefore, this is the. But what is dt dash x? This is T dash, as you can see, this is T dash. This is where A was located earlier. A was located earlier. Therefore, dt dash x is nothing but dt of A. Therefore, this is equal to dt of x times f of x plus dt of A times f of A minus dt of A times f of x minus dt of x times f of A. Okay. So, this term is replaced here and this term is replaced here. What was x in T is A in T dash. Therefore, okay, dt dash x equal to dt of A. Here is dt dash of x. This is T dash, this is x, and that is where A was there in T, same path. Therefore, dt dash of x is dt of A. Similarly, other. So, eliminate T dash and bring everything to T, and now you can take dta common, f of A minus dt A times f of A minus f of x plus now you can use dtx times f of x minus f of A. That is equal to f of A minus f of x times f of A minus n. So, dta minus dtx. X is the one with least frequency, therefore, this is greater than or equal to 0. A is the node at the deepest level. Level of x is slightly higher, therefore, this also, which means Ct is greater than or equal to Ct dash. We have shown that Ct is equal to Ct dash. In a similar way, you can exchange y with b, and therefore what you can do is you can transform the x the a b. I transform this into a b x and y. X and y has been brought as sibling, and they are brought to the lowest level. They are brought to the lowest level. So even if the optimal structure does not look like the greedy solution, I can make it look like greedy solution by this argument. Okay. But this is only a thought experiment. You are not going to implement or do anything. It is a proof, just for mathematical proof. Okay. That means the lowest ones, lowest frequency one are associated with deepest leaf. Very low character, it is associated with a node that is very deep, therefore its code word may be long, that is okay. The higher the frequency, lower will be the level. But that is what we are doing in Huffman's code. What Huffman? Take the two smallest frequency one, put them together. So initially there are n nodes, then there will be n minus 2 nodes and one super node. Then you will have n minus 3 nodes with C super node. So if you proceed like this, you can see that you are constructing the entire minimum spanning tree, which is going to look just like the greedy solution, right. Whatever greedy has done is now justified, because if it is not, I can exchange and then I can always make my optimal solution look like this. Therefore greedy works. So you can see the very indirect way in which things are done. Okay, it is very subtle. It is an art. But this beautiful theorem shows how the algorithmic thinking is built on mathematical thinking. Okay, your prescribed book, Corman has a chapter on greedy algorithm. And there he is discussing this problem, okay, very clearly with all illustrative examples, and in fact my numbers are pulled out from there. So when you go and refer the book, you will not have any difficulty in following the materials up. Okay. So I stop at this point the discussions related to Huffman code. We will continue our discussions on minimums on greedy strategy, but on a very important problem called minimum spanning tree algorithm. Okay, thank you.